All right, so now let's take this opportunity to go ahead and review basically the entire unit here in Chapter 10. There's a lot to it: the moles conversions, percent composition, empirical formulas, molecular formulas. So let's just quickly go through this. 17 grams of NaCl to moles. Well, 17 grams NaCl, and I'm going to convert to moles. X, line, grams, moles, 1. That's kind of how I do it. I X-line it, I put the labels in, and then I think about the numbers. The number for moles is always 1. Periodic table, sodium is 23, chlorine is 35.5, so there's your 58.5. Let me go ahead and get that calculator. 17 divided by, because that 58.5 was in the denominator, 58.5, 0.29. All right, so 0.29 moles of NaCl. I'm a big fan of the label, of the box. Okay, then we're going to convert and kind of move this over here, I guess, a little bit. 3.85 moles of water to molecules. So 3.85 moles to molecules, X line, moles in the bottom, molecules on top, 1. Again, kind of a automatic, I go through it. The molecules conversion number is 6.02 times 10 to the 23rd. It's in the numerator, so I'm going to be multiplying. Let's go ahead and do that. 3.85 times 6.02 EE 23 equals 2.32 times 10 to the 24th. 2.32 times 10 to the 24th molecules of H2O. There I am there. How about liters of neon to moles? So 75.8 liters of neon, X line, liters, moles, 1. Again, just without even really spending much time thinking about it. The liters conversion factor is 22.4. It's in the denominator, so I'm going to divide 75.8 by 22.4. Let's go ahead and do that. 75.8 divided by 22.4 equals 3.38. So 3.38. 3.38 moles, and again, of neon. Nice little box around it. My last one is a multi-step, grams of copper to atoms of copper. I'm going to just go ahead and review our little flow. I'm a big fan of this. We can go mass in grams. We can go particles, and we can go liters. So there I am. I'm starting with grams. So 32.17 grams of copper, and let's change it to moles, and then I'll go to particles. So X line, grams, moles, 1. I look up copper on the periodic table, 63.5. So 32.17 is my number. Clear. 32.17 divided by 63.5. I get 0.51. Alrighty. 0.51 moles. Bring that down where I get a little bit more room. And now X line, moles, atoms, 1, 6.02 times 10 to the 23rd. And I'll go ahead and pull up my calculator again. Times 6.02, straight to the E, 23, equals 3.05 times 10 to the 23rd. 3.05 times 10 to the 23rd atoms. Nice box around that one. So there's those conversions. I want to move right along here. So I'm going to erase that and go to the next slide. What is the percent composition by mass of each atom in the following? Okay, well, let's go ahead and find out what they are. Well, magnesium is 24. There's only one of them. Nitrogen is 14, and there are 2 of them, so that'd be 28. And oxygen is 16, and there are 6 of them. So let me go ahead and just, rather than bringing up that calculator, I think it'll be a lot quicker if I just go, the 16 times 6, of course, is 96. Add those all up. And so plus 28 plus 24, I get 148. So the magnesium one is going to be 24 over 148. Nitrogen would be 28 over 148. And oxygen is 96 over 148. So 24 divided by 148. And of course times 100 for each of them. 16.2% magnesium. 28 divided by 148. 18.9% nitrogen. And 96 divided by 148 is 64.9% oxygen. They pretty much add up to 100, but basically there it is. Empirical formula for the following. This next question. Well, this is a 2 to 2 to 4 ratio. We can simplify that to 1 to 1 to 2. So the empirical formula, KCO2. Simple enough. This one is a 2 to 1 to 7, which means it's already simplified. So, whoops, it's Na. It's going to remain the same. Same empirical formula. Molecular formula for the following. To do A here, you take the the molar mass which is given, divided by the empirical formula mass. Carbon is 12 and hydrogen is 1, and there are 2 of them, so that's 14. I get 10, so that's going to be the factor I multiply it by. C10H, whoops, that doesn't look like a 20. C10H20 is the molecular formula for that first one. The second one, I have 350 divided by, carbon is 12 and there are 2 of them, so that's 24. Hydrogen is 3 more because there's 1 and there are 3 of them, and then 16. So if I add that up, that is 43. So 350 divided by 43 equals 8.14, which we round to 8. And so C16H24O8 would be the molecular formula for that one. Okay. The last slide is going to be molecular and empirical formulas. I'll go ahead and solve for that one. And again, I don't want to take too long, but it's the last little review, so we might as well. What is the empirical and molecular formulas for the compound that is 60% silver? I'm going to write, whoops, I'm going to write my 60% silver, 32% phosphorus, and 8% sulfur. And the molar mass is that 1425. All right, first step, convert that to grams. 60 grams silver, 32 grams phosphorus, 8 grams sulfur. Once I have my grams, change it to moles. X line, grams, moles. X line, grams, moles. X line, grams, moles. 1, 1, 1. Now I look them up on the periodic table. Silver is 108. Or 107, right? 108. Phosphorus is 31, and sulfur is 32. Okay. 60 divided by 108 is 0.56 moles of silver. 32 divided by 31, 1.03 moles of phosphorus. And 8 divided by 32, 0.25 moles of sulfur. My next step is to divide by the smallest. 0.25. 0.25, which gives me 1, obviously, in that one. 1.03, I know it's going to be about 4, right? Divided by 0.25, 4.12, and 0.56 divided by 0.25, 2.24. These get rounded to 2, 4, and 1. So silver is 2, phosphorus is 4, sulfur is 1. Now, to determine the molecular formula, I take that given 1425, divide that by my empirical formula mass. Silver is 108, 108. And I have 2 of them. Add that to phosphorus, which is 31, and I have 4 of them. Add that to 32. When I add that all up, I get 372. Do that dividing. 3.84. Round it to 4. This becomes our factor, Ag8P16S4. There would be my empirical and my molecular formulas.